Yeah, hi everyone. Good evening. Welcome to week number 10 of Computational Complexity course on NPTEL. Again, my name is Habirdeep Rai and I'm a PMRF PhD scholar from IIT Madras. Let's get back directly into business. Okay. Last week we saw some concepts from counting, a bit of circuits, right? And this week was completely on counting. So this week's topics are namely um, sharp P completeness, okay, and the fact that permanent is sharp P complete, and the next result is Toda's theorem. Okay, and permanent is sharp P complete. And I'll talk about sharp P class and so on. And Toda's theorem is what it says that. Um, the polynomial hierarchy is contained in p to the sharp. Okay. So yeah, let's go on defining what all this is. Okay. And just to recall, what is sharp p? Now we are on in the realm of counting. Okay. So there are several kinds of problems. We can have like computational problems can be of several kinds. Okay. So you have computational problems. Okay, and they can be of several kinds. And but roughly we can categorize them into two types. Okay, roughly we can categorize them into two types, and one is decision problems. Okay, and what are decision problems? They are yes or no questions. For example, is this circuit satisfiable? Is there a path between vertices S and T, and so on? All these problems that we saw until now. Okay, does the graph have a perfect matching and so on? So these are all decision problems. And the other kind of problem is what is called a search problem. Okay, what is the search problem? The search problem says find uh, find a result satisfying some property. Let's say property P. Okay. Now, search problems can also be of different kinds, right? So, search problem could be something like, say, an optimization problem, and search problem could be something like, a maximization problem where there's a single parameter. Optimization could be several parameters, right? And and similarly, there is something called counting. Okay, and these are of course very much closely related to each other. And there is a simple search itself. Search, like for example, a linear search kind of thing, where you are given a list, you are given an array, and you are told to search whether this particular element is there or not. So that is not like an optimization problem or a maximization problem or even a counting problem, right? But these all fall into this larger class of search problems.
So I have a
Okay.
question here.
Yeah.
That since the every optimization problem can be viewed as a decision class problem, so why do we require such a separate classification?
Yeah, right. So every problem can be viewed as a decision problem. Well, can you give an example?
Like say if we need to find the vertex cover, so this is an optimization problem. Or let us say if I need to find a click, then this is an optimization problem. And now if I
Wait,
look
wait.
for
How
its
how how how
decision.
is finding a vertex cover optimization problem in?
Okay, so getting the minimum vertex cover is an optimization problem, or
Okay,
getting
minimum.
the
Sure,
maximal click is an optimization problem.
sure.
And now, if I modify this problem as does it exist a click of the size say greater than 500, then it becomes a decision class problem. So my
Sure.
perception is that if I need to get the answer of the decision variant, I need to solve the problem first. To solve the optimization problem first. So therefore, every optimization problem can be viewed as a decision class problem. Is this argument correct?
Yeah, it is correct in a. It is correct that every optimization problem can be solved by decision problem. Okay,
And vice versa?
and yeah, and every decision problem can also be solved by optimization problems, but the trade-offs are different. Okay, I'll give you an example.
Okay, okay.
Okay, I'll give you an example. Um, let's look at an example where there is a large solution space, which is something like yeah. Okay, okay. Let's do reachability. Okay. Or oh yeah. Okay, okay. Let's do yeah. Let's do reachability. Or vertex cover is also not bad actually because uh, yeah. Let's do clicks. Yeah. Okay. Let's do click. So what is click? The decision variant of click is uh, G and K such that G contains a click of size K. Okay, this is the decision version. Now, what is the not the let's not say the optimization problem, or yeah, let's say the optimization problem version. Something like find okay optimization. So I'll call it O click. Okay, is again G K. Okay, not K anymore. Is I cannot write it like this. I need to say something like input is a graph G and output is um, click Q such that there does not exist any Q prime such that Q prime is smaller than size of Q. Right? Well, okay. So this is the optimization version. This is the decision version. Now let's see how we can um, uh, solve click using O click. Okay, solve click using O click. Let's try that. Okay. So remember again, click says you are given a graph. Okay, I want to check if it contains a click of size k. O click is given a graph. I want to find the smallest click there. Okay, I want to find the smallest click there. Okay, now or not the smallest click. Let's say the largest click. Okay. Smallest click does not make sense because the smallest click would be just like finding triangles or something like that. Okay, so yeah, so finding the largest click. Now what I do is, okay, here is an algorithm for click. I'll call it click solver. Okay, what is an input? Input is G and a key. Now what do I do? I just simply run O click solver on G and say the suppose output is stored in um, y. Okay. I'll copy this and go to next page. Okay. Okay. Simply just the algorithm just runs the optimal algorithm for click. Okay. And solver on G and outputs y, or let me not call it y. Let me call it Q, where Q is a click. Q is a set of vertices. Okay. Now what do I do? I simply check if size of that click, okay, is greater than k, greater than equal to k. If yes, then I'll output yes. If no, then I'll output no. Because if what I want to do is I want to find the largest click in the graph. I found the largest click. If the size of the click is 5 and all the vertices are connected to each other, then obviously there will be a smaller click of size 4, and then there will be a smaller click of size 3 and 2 and 1. Right? If you take a complete graph on 5 vertices, and if you take a complete graph on 5 vertices and then check for a k4, you will always find a k4. You will always find a k3, which is a c3, and so on. So uh, uh, this way you can see that if I simply check if there is a click, large click, okay, which is larger than k, I am guaranteed that there will always be a click of size k, which solves the decision problem
Yes.
version for the yes instance. Right now, for the no instance, let's say the click it outputs is a click of size smaller than k, then it cannot be that there exists a click on that graph which is of size k, because otherwise my optimal click algorithm would have outputted that particular click, right, of size k or greater.
Yes. Yes.
Right. So you can see that, and how many queries did it, how many calls did it require to the subroutine? Only one. Let's say this,
Right.
right? Let's say this, okay. So only one call. So let's say if click is an oracle, if click, sorry, o click is an oracle, then I mean it just requires one oracle query, right?
Yes.
So, or if you don't want to see it as an oracle, see it as a subroutine, then also fine. If o-click runs in polynomial time, then this entire thing will run in polynomial time. Well and good. So, as long as I have uh, not just optimization, in fact, any search problem, okay, efficient search problem leads to an efficient decision problem. Okay, efficient problem,
Yes.
yeah, leads to a efficient decision problem. I can give you another example also, and uh, that would be, let's say I'm not looking for an optimization problem, I'm doing a counting problem. Counting problem. Okay. That would be um, okay, take any sort of NP complete problem. Say okay, say okay, SAT is there. Okay, let's take SAT. Okay, take any counting problem. Say sharp SAT. Okay, what is sharp SAT? Sharp SAT is all those formulas such that phi is, oh sorry, sharp SAT is um, the input is a formula and output is number of satisfying assignments to phi. Okay, input is a formula and
Yes.
right assignments to 5. So I want to solve SAT using sharp SAT solver. Let's say there is an efficient sharp SAT solver. How do I do it?
So clearly, I mean, in order to solve the sharp set, I should know at least one solution. And when I know at least one solution, so set problem is automatically solved.
Exactly. So what is my algorithm to solve SAT
Uh,
given the
so
constraint?
yeah, so it would be that I will run the algorithm, say for the sharp set solver once, only once.
Hmm.
Once I get say the count
Hmm.
greater than 0, so
Yeah.
that shows that yes, there exists a solution.
Yeah. That's right. Yeah. Let's say the output is M. Then what do I do? Check if M is greater than 0. If yes, output yes. Otherwise no. Now, if you have an efficient SAT solver, then you can solve SAT also easily. Right.
Yes, so if I have an efficient set solvers, then yes, so I will run the set solvers multiple times. But
Oh, sorry.
how
Yeah,
many
sorry.
times
If,
I
if I
can
have
run?
an efficient sharp SAT solver, I can solve
Yes,
SAT
yes,
easily.
yes,
Yeah,
yes,
that's what
yes.
I'm.
That is
Sorry.
true. That is true.
So okay. So we have this that counting version. Okay, is at least as hard as decision version.
Right, right.
Yeah, with these examples. Now let's look at the opposite case that you are talking about. That is, let's go the other way. Decision version to solve SAT, and that you've answered. Decision version to counting version to find. Yeah. So yeah, Suraj, we are talking about the opposite case when we are talking about solving decision version. Okay, to sorry, decision version to counting version, which means that I have efficient decision version. Can I come up with efficient counting version? Now that is another question, right? So let's say I can suppose um, P equals NP. So SAT is in P. So I have a polynomial times SAT solver. Um, can I also find? Can I find number of satisfying assignments to a formula 5? That is nothing but sharp SAT. Can I do that easily? That is the question. Okay.
So I do not think that it would be that easy because even if the set runs in the polynomial time, then I do not know till how much. I mean, how many times I'll keep on getting the satisfiable things.
Exactly. So in the worst case, what you do is you go across all. Okay, the naive algorithm would be um, just go across 0 1 to the n and check if, let's call it y, check if phi of y is in SAT using that efficient SAT solver. And how much time will this take? This will take some exponential time times some polynomial.
Yes.
So now we already see that it's not trivial, right? Well, and there are some gray areas also. Okay, for example, searching for a satisfying assignment. We already saw that that is possible. Searching for a satisfying assignment, it is a search problem. It is a search
Yes.
problem,
Yes.
right? And it is possible due to the self-reducibility of SAT if SAT is solvable efficiently. We saw that. So
Right.
yeah,
Right.
there
Right.
are, you're right. There are these gray areas, but so that is for the search problem, and there are examples where the search problems are easy. By search, I mean searching for that exact property what decision is based on, but the counting version. Okay, the counting version. So I'll rather not call it the search version. Okay, I'll call it um, I'll call it the functional version. Okay, this is beyond decision. Okay, let's call it functional problems. And these are so and even though search was easy, counting is difficult. So now we have that efficient decision version may not lead to an efficient counting version. So it seems as if um, the conjecture is that this counting version is strictly more harder than decision version. And now we have enough reason to study counting version. If it was trivial, if studying decision version was enough, then we would be well and happy. But it is not enough because counting version looks like a more non-trivial class. Okay, and so it makes sense to give it enough importance, right? Yeah. So gray area means like set for satisfying assignment or search problem. So what I meant by gray area means that Suraj, this areas where the search problem is as efficient as the decision version. Okay, if the decision version is solvable easily, then the search version also solvable easily. Okay, decision version is solvable easily, then the search version, the functional version, also solvable easily. Those kind of areas, that is what I mean. For example, if SAT has an efficient algorithm, then um, if SAT has an efficient algorithm, then the finding a satisfying assignment is also can be done efficiently using the self-reducibility. You remember that tree thing we did, right? But then again, counting is not as easy. We don't know how to do it. So that is what I meant. Okay. So that is what I meant by the gray area. And and see, it's so you might say something like uh, okay, so before I get into it, okay, everything fine, Suraj?
Yes.
Okay. So yeah, now let's get into the counting classes. Okay. So so one is a very simple class. Okay, it's what is called FP. Okay, and F stands for functional P. Okay, so okay, have you? I mean, you may have thought of this, right? So this is the search version of P. Okay, this is the search version of P. So you may have thought something like, a lot of computational problems that we do in real life are not really always decision problems, right? I mean, the programs that you write in C, Java, whatever, okay, to solve problems, they are not always yes or no questions. Okay, in fact, most of the times you are required to output something. So, what is the complexity class that captures all these efficient algorithms that solve these kind of problems? And that is exactly functional P. Okay, functional P is those problems that uh, those problems that can be solved by polynomial time Turing machines, okay, with um, um, okay, can be solved by polynomial time Turing machines. Uh, those not just problems, search problems that can be solved by polynomial time Turing machines. What does that mean? That Turing machine has an output tape where result is written. Okay. For example, if I say the search question, okay. So for example, the let's call it search, okay, and this is given an array A and element E or K. Uh, K belongs to A. Now this is a classic problem that we do in programming, right? Using binary search, linear search, whatever. And this is the first problem. This is the decision problem. So this guy is in P. Linear search is in P, right? And search. Now here is a different version. Given is an array A, and K is a natural number, say. Okay. Output. Okay. Output is I such that AI equals K means that at ith position I have K, that is output the index of the element, and let's say -1 otherwise. So is this possible to do in polynomial time? This search, I'll call it F search. Is it possible to do in polynomial time? You're given an array and an element, and you need to output the index.
Oh, yes, so because I mean, sorting can be carried out in the polynomial time for any number of the elements, any finite number of the elements. And once the sorting is ready, so later on we can always perform the search on it in the polynomial time. We can go for the binary search. So I think this entire thing can be done in the polynomial time.
Yeah. If I don't do sorting, is it still possible?
So if I yes, it's still possible because
Yeah.
I'll have to go for one scan only, and then I can find the element. Yeah.
That's right. Right. So, and this is not a yes or no answer. Okay, in this S search was a yes or no answer. F search is not a yes or no answer, and this is in FP. Okay, the algorithm can be thought of as a Turing machine with an output tape where my final natural number will be written there. Okay, in binary, and yeah, basically you go to left to right, scan, check whether that any index contains that, and that index I just copy it into the output table of the Turing machine. But I'm not only writing 1 or 0 on the output tape. I'm writing some non-trivial string out there. So this is what FP is. Okay. So FP is very similar to P. Okay. And comparing FP and P is not very straightforward because they talk about different things. One is talking about yes or no. One is talking about outputting the answer. But of course, it is not. Firstly, if you can do FP, then you can do P. If there is an efficient algorithm similar to before, if there is an efficient algorithm that can find a solution, then there is an efficient algorithm that will tell you the existence of a solution also. But if you have an efficient algorithm which tells the existence of a solution, it is not straightforward that it is not known whether that, okay, you can also search it in polynomial time. It is not known. Okay, because say P does some kind of a probabilistic argument that says that, oh, the probability that the solution is there is greater than 0. Okay, it has a probabilistic answer that since it's greater than 0, there should be at least one viable solution. But finding it, that is not always clear. It so happens that the algorithm for our search ends up finding that particular index and then outputting the index. So therefore, it was straightforward. So it is not clear, but FP, it is believed that FP is very close to P. Okay, FP is the P of the functional world. Okay, similarly, you can talk about FNP. Okay, that is non-determinism, non-efficient non-deterministic algorithm that does a search. Okay.
But then I think that FP should be exactly equals to P, and why not? Because once we know that element, I mean, is there, right? We should be always be able to print yes or no depending.
Why?
So say
You know it
if we
is there.
find, yeah, so if we find that, so in the FP, I mean, we can efficiently carry out the search, and the searched element, I mean, its index will get displayed. That
But
is the
but
only
but
thing.
the search space may be very large, no?
So if the search space is very large, then neither this F search would be running in the polynomial
Oh
time.
no. I'm not talking about the search problem. For search problem and F search problem, they are, yeah. I agree that they are like the same thing.
Okay, okay,
I mean, for a
then where is the
general
issue?
For a general P algorithm, okay, or a general P problem, is it
Yes.
identical to a general FP problem? Will the same algorithm still work to find the searching? That is not clear. Because that particular P
Actually,
algorithm may be doing some very strange stuff to say that, oh, okay, so at least one solution should exist, right? It may be doing some kind of probabilistic arguments.
oh, I see. So you mean to say that FP is same as, I mean, FP implies P. However, P does not imply FP. Is this
Yeah,
so?
yeah,
Okay,
yeah.
okay.
At least this is not known, okay? That if you
Yes,
have an
yes, I
efficient P
understood.
algorithm, then you have an efficient FP algorithm also.
But still, I have some reservation and some
Yeah,
hesitation here,
yeah.
because say any algorithm and which belongs to the P class won't be using the probabilistic features, won't
Oh,
be
wait.
saying anything with
Oh,
certain
it could
probability. It would
calculate
it
probability, right? I don't mean that it's using some randomizations. Okay, I'm not saying it's tossing random bits. I'm saying that it
yes.
could calculate probabilities.
Oh yes, it may calculate probabilities, and then through some other route, it may reach to the conclusion that whether the value is yes or no without
Yeah,
actually searching the element. It may so
exactly,
happen.
exactly,
Oh, I
exactly.
see. I see. Yes, yes. Now I understood. Yeah.
Right.
Thanks. Yeah.
Okay. So you have that, but despite this, okay, um, but it's like comparing apples and oranges, right? Because at the end, you are comparing a decision variant and a search variant, where the search variant is clearly at least as powerful as the decision variant. So you cannot say that, oh, P is contained in FP, FP is contained in P, and so on and so forth. You cannot say that. So even if I build, let's say, a landscape of um, let's say I build a landscape of, P is contained in NP, and NP is contained in let's say P space, and so on, and then I cannot suddenly bring, sharp P or FP or whatever. So it does not make sense. It does not fit into the same landscape. This falls into a separate a separate counting landscape or functional landscape, whatever. Okay, so it does not make sense to do that. So we cannot do that, but we'll come to that now. We'll come to that. Now, I first want to introduce sharp P now. Okay. Now we want to find. We are interested in not searching the solution. We are interested in finding number of solutions, number of valid solutions, which is nothing but number of certificates. Okay, which is close to, not exactly equal, but it's close to certificates. It may not always be equal. Number of valid solution, which is close to number of certificates. We don't want to count this number of certificates. Is there any possible analysis for that? That is the question. Now we have the idea of the sharp P class, and you can sort of see that this is a variation of NP. Okay, this is a generalization of NP. Okay, sharp P. Okay, is the class, okay, of functions. Okay, now we'll talk about functions. Okay, f of x is in sharp P if there exists a non-deterministic Turing machine, okay, such that on input x, okay, on input x, um, non-deterministic Turing machine M has f of x many accepting paths. Okay, and m runs in polynomial time. So remember in NP what used to happen? It used to make all these non-deterministic guesses on the way, and even if there is at least one accepting path, and it may be that there are more accepting paths, okay, at least one accepting path it used to accept, right? Now we are interested in how many such accepting paths are there. In other words, how many certificates are there? Because that NP was guessing the certificate, right? And this is of polynomial length, and this was nothing but guessing the certificate. And let's just, without loss of generality, say that everything to the left is reject, accept, and everything to the right is reject without loss of generality. Of course, this may not always happen, quite unlikely to happen, but this is okay represented by sometimes by this hash accepting m1x. Okay, number of accepting assignments. This is equal to f of x. And now I have this special class of problems, okay, such that there are machines, and I want to compute f of x, but I do it in a very strange way. Okay, f of x is in sharp p if I have a non-deterministic machine, okay, such that on an input x, on that input x, same input x, the number of accepting paths is equal to f of x for
So
all
it
x.
ideally, yeah, ideally it should have been called then hash of NP instead of hash of P, because the Turing machine itself is non-deterministic, even though it is running in the polynomial time.
Yeah, yeah,
But
yeah.
yes,
It There could have been a better notation for it. I agree. Sharp P, it may be mistook for a deterministic class.
yes,
Yeah,
yes,
yeah. But if we look at from number of certificates way, then we can convince ourselves that okay, so this requires non-determinism.
yeah, okay, okay, yeah.
Okay. So for example, there is something called PP, f of x. Sorry, PP, PP. Okay. So f of x is in PP if there exists a non-deterministic Turing machine M, okay, such that for all x, okay, um, for such that for all x, x is accepted if there exists exactly half accepting paths.
And this PP stands for what? Probabilistic polynomial? No, no, no.
Yeah,
It is
probabilistic polynomial. Okay,
okay.
and for example, BPP is contained in PP, so that is yeah, and so on. But this is the different kind of things that complexity theorists were studying around that time, and so NP is that these are all actually some kind of generalization of NP. So NP is talking about a single accepting path. What if we are trying to count the number of paths? Okay, in other words, one motivation would be satisfiability. How many inputs are there that actually satisfy the formula? I'm not just interested in that. I'm not just interested in checking whether it satisfies or not. How many inputs are there? Okay, that satisfy it, and so on and so forth. And you can actually show that, okay, using Coq-Levin, you can actually show that. Okay, now we have the idea of reductions here. So how do you do reductions here? Okay, so f and g, okay, are functions, okay, okay, or rather I'll say something like sigma star, but any sigma star can be again interpreted as natural number, so I think this is fine. So we say f reduces to g, okay, if for all x has a natural number, okay, and x can equivalently be thought of as a string also, so no problem. For all x as a natural number, f of x is in um, fp, so I'll call it fp reduces to g, fp to the um g of x, not necessarily x, yeah, g. Given oracle access to g, so I'm using g like a subroutine here. Okay, I want an efficient polynomial time Turing machine. Why fp? Why didn't I do something like p? Why did I do something like p? Because if it is in p, then it is only able to decide 0 and 1. That is what it means. And f that this function f goes from natural number to natural number. Okay, so that's why fp. Okay, so this is reduction. Now I can talk about completeness also now. Sharp p completeness. Okay, sharp p completeness. Let's say I take f. Okay, is sharp p complete if, what is the first condition in any completeness um, statement?
So that problem should belong to that complexity class.
Exactly.
And the problem should be I mean that complexity hard problem.
Exactly. So hardness means every problem should reduce to
Yes.
that problem.
Yes.
Every problem in that class. Okay. For all g such that g is an fp, sharp p. Okay. We have that. Um, we have sharp fp reduces to g. Okay, and this is nothing but um, f of x is in fp of g. No, sorry, what am I doing? F reduces to g reduces to f. It should be everything reduces to f. G reduces to f. Everything in fp reduces to f, which is nothing but you can decide g with oracle access to f. Okay.
Yes. Yes. And what could be the meaning of say reducing g to f would mean that I pick any instance which of the g, and then I can rephrase that instance by applying the function f in so I can rephrase that instance in such a way so gx belongs to this thing. So ideally it should be, since g is the I mean what does it mean? Actually the here the problem is happening because the name of the reduction function and the name of the problem, I mean, both are same. So it could be something else. Say so g is reduces to the f if there exists a function, say something else, a t kind of the function, such that every instance of the problem g can be rephrased as an instance of the problem f, and such a reduction should belong to the fp thing. I mean to say.
But yeah. But that is you are going close to many one reductions. You are
So
transforming the problem into another problem, right?
yes, yes. And what is happening here in this case,
But
by the
this
way?
is Turing reductions.
Oh, I see.
So you
I
can do
see.
many queries on several different kind of queries.
So actually, I forgot the difference in between the Turing reduction and the car prediction. So
Okay,
because whatever I remember is the car prediction, I think.
sure. Card reduction is that A reduces to B Okay, let's say polynomial time. Okay, card reduction means that there exists a sigma, okay, such that for all x in L A, for all x in say 0 1 to the star whatever, uh, x is in A if and only if sigma of x is in B. This is what is the transfer. Sigma does a single transformation. So this is a
Yes,
very
yes.
restricted thing. Okay. But what is a Turing reduction? It talks about, what if I'm allowed to use B several times. Now you have the concept of oracles. Okay.
I could not hear you at this point. Yeah. What
So
did you say?
I said Turing reductions says that let's not be too harsh. Okay. Let us relax. That we can use the B solver only once. Okay. So Turing reduction means that A Turing reduces to Turing polynomial time reduces to B. Okay. Means that um, okay, so polynomial time, right? So it means that A given access to B is in P. Now what does this mean? This means that B given as oracle, okay, A, okay, given as oracle, um, so I won't write it A given A to the power B. Sorry. It's a bit confusing. This means I can solve A, okay, if I am allowed polynomially many queries to Oracle B. And these queries may be not the same queries over and over again. That does not even make sense, but it could be different kind of queries. And the queries will be of the form is Q1 in B, is Q2 in B, and is Q3 in B, and so on. So these are the kind of queries that you make.
Yes, yes. Now I
Okay.
remember. Yeah.
Yeah. So this is what Turing reduction is. Okay.
So
And
how such a reduction is happening here? I mean, in this case.
in this case, I'm given Oracle access to F.
So
So I
G is getting reduced to FP to F if and only if G of X is an element of this. I mean, this
yeah.
line is not clear
So
actually.
yeah, this I was a bit casual here. I just meant that they are same. Okay. So
So what does
this
it mean? What does it mean that G of X? What does it mean? So G may be making, I mean, as many queries as G wants to the F. It's
yeah.
okay. But why the G of X then? I mean, the G of X is an element. Moreover, this is FP
Yeah.
kind
So
of a
sorry.
thing.
I shouldn't be writing X. There is no X. Sorry. Yeah. I should be writing just G.
Yes, G belongs to, and then this. Oh, I see. So FP raised to the power of F kind of the thing. Is this like
Yeah.
this? Oh, I see. Yes, yes. Now I understood. Yes.
Okay.
So G would be querying to F multiple times, and but then by following this constraint of the FP thing.
Yeah.
Yes, yes. I understood. Yeah.
FP simply means polynomial many queries are allowed.
Polynomial many queries are allowed, or whichever Turing machine is executing this FP
Runs in
would be
polynomial time.
taking runs in the polynomial. Yeah, I understood this thing. Yeah.
Okay. So now you understand why this is enough for sharp P completeness. Okay. Okay. So now, so you got what these reductions are, and Now, because now, but that was a good question. That why are we doing Turing reductions only? Why not do menu and reduction? Right. And well, Turing reduction allows you to be more relaxed. Okay, so you can put more things in the sharp p complete basket. Okay, otherwise, do such functions even exist? Okay, and that leads to what is called parsimonious reductions. Okay, now what is parsimonious reductions? Okay, this simply means that count is preserved. What does it mean? I have so I have that A reduces to B. Let's say two problems. A reduces to B, and both are counting problems. A, B are counting problems. Okay, a reduction parsim. Okay, and a reduction A reduces to B. Okay, where A, B are counting problems is said to be parsimonious. Okay, if okay number of solutions to A is equal to the number of solutions to B. Okay, in other words, the reduction preserves the count.
Yes,
Okay,
yes, that's true. But number of reductions are being preserved. I mean,
no, no,
the count
yeah,
is being preserved here. That's okay. But count for instances. I mean, for all the instances, the count is getting preserved. I mean, this seems to be very strong and very difficult reduction. Then,
it looks to be
uh,
strong and it looks to be difficult, but these reductions exist,
oh, I see, I see.
and
All right, yeah.
they there are very good examples. I mean, for example, yeah, if you look at that, proving, for example, this sharp sat problem. Okay, sharp sat problem, we can see that it is in sharp p, right? Why is sharp sat in sharp p?
Yes, so because I mean, according to the definition, we can have a non-deterministic Turing machine, and which runs in the polynomial time, and that will give me the count of the assignments, and which makes a satisfiability problem. I mean, which
Yeah,
makes the problem satisfiable. Yeah.
exactly. This is the same algorithm for, let's say, non-deterministic sat will work here, but sharp sat is also sharp p complete. Sharp sat is also sharp p complete.
Yes, and this reminds me that since every algorithm on this, I mean, on this planet, can be encoded as a Boolean formula. So, what does it mean that since I mean the sharp set means how many solutions are there? So basically, I'm asking that okay, so how many solutions any algorithm, I mean, can have? So there would be probably there would be a one-to-one correspondence in between the number of the satisfying assignments and the number of solutions of an algorithm.
Not an algorithm, a polynomial type algorithm.
Not an algorithm, but what? Uh,
Not any
what?
algorithm, but polynomial time algorithms.
Yes, yes, polynomial time
But why
algorithm.
would you say
Right.
that? Why would you say that it corresponds to sharp set?
So I said that because every algorithm can be encoded as a Boolean formula according to the Cook-Levin thing. And now, since we have,
Exactly.
so if we know that how many solutions are there of a satisfiability problem, then corresponding to an algorithm, there would be a satisfiability problem. So if I can find the count of the solution of the satisfiability problem, then I would be having a count of the solutions of an algorithm. I
Yeah,
mean,
that is close. That is close. The fact that sharp is in sharp is sharply complete. Okay, that it is sharply hard. Okay, is proved by using Cook-Levin reduction. Okay, is proved by
okay,
using the Cook-Levin reduction. Any because Sharpie is finally a non-deterministic Turing machine. Okay, any Sharpie language can be characterized by Sharpie. Sorry, any non-deterministic Turing machine can be characterized by a Turing machine. Okay, and that Turing machine can be converted to a that verified Turing machine can be converted to a SAT instance. And you are right to say that the number of satisfying assignments, okay, that simply saying that, okay, will actually prove the Sharpie completeness. But we can say something additional. That is that not only is the reduction there exists, the reduction is also parsimonious. The Cook-Levin reduction preserves the number of solutions.
how and why?
You should, yeah, but I won't go into the deep details there. How and why? Because look at the possible certificates. Okay, I'll just say that look at the possible certificates to a non-deterministic algorithm. All the good certificates, that is, all the valid certificates. None of the certificates are lost when you are converting it into a formula.
I could not hear that. So when I'm converting what? So number of the certificates, good certificates will get preserved when.
Yeah, none of them are lost when you convert it into a formula. There is, like you said, there is a one-to-one correspondence between a certificate and a satisfying assignment.
Yes, yes,
So that is the first example of a parsimonious reduction.
yes.
And then later you have this permanent, okay, permanent perfect matchings and so on and so forth, and all of them have parsimonious reductions with each
Okay,
other.
okay.
Okay, and but of course there are we know a lot of cases when we don't know parsimonious reductions, but they are but okay, maybe it's a good question to pursue that whether all Sharpie complete problems can be reduced parsimoniously within each other and so on. Okay, and there are examples where there are given reductions, but the reduction is not parsimonious, but it can be converted into a parsimonious one, and so on and so forth. So, but that is about parsimonious reductions. Now, so I told you, right, there is this decision world, and there is this counting world, counting and search world, and we want to and what else have we? Oh, we've seen the circuit world, right? And decision world is something like NP is contained in P is contained and P is contained in, say, P space and so on. And here we have NC1 contains AC0 is containing NC AC1 and so on, and all these classes. And what we want to do is we want to build bridges between them. Can we build bridges between them? Okay, and A bridge is the uniformity argument between circuit and precision. For example, something like um, NC1 is contained in L. Okay, and BPP is in P slash poly. Right, and and anything else, and you can relate with NC2 and so on. Is there anything else? Well, using uniformity, you can see some other things. So, for example, P equals P size, and so on and so forth. So these are some theorems that show build bridges between the two worlds. Now, question is, can we build some kind of bridges between? Of course, we cannot bring them directly. One is a subset of another, and so on. For example, here you kind of can. You can add the uniform, okay, L uniform NC is contained in L. Now you can contain one in the other because you can compute NC1 in log space. This kind of NC1 in log space, but can you build? Okay, you cannot do something like that sort of directly. Okay, but one such bridge between the counting world and the decision world is something that is very surprising, and that is something called Toda's theorem. And what is Toda's theorem? It is that P is contained in, not P, PH is contained in P to the sharp P. Okay.
Yes, yes, but then I mean P. I mean, how to pronounce it? P raised to the power or what? I mean, what is the right way of calling this? I mean,
Usually people say, yeah, no, not, yeah, you can say raised to the power also, but people usually say to the power, to the sharp P.
okay. So P to the sharp P.
Yeah.
I mean, this is something which is so very probably unrealistic kind of the thing. Why so? Because sharp P itself is non-deterministic.
Hmm.
And yes, that's true. That's true. Yeah, pH is the entire hierarchy thing.
Yeah.
Uh,
I mean, it is a
so
bit surprising. That is true because pH is actually a very large. I mean, it is believed to be a very large class unless a collapse happens. Okay,
yes,
and
yes.
sharp P seems to be very similar to close to NP, and
Yes.
NP is sitting at the bottom of pH's hierarchy. Okay, almost at the bottom. And
Right. Right.
to say that if I have access to sharp P oracles, say permanent or sharp sat, whatever, then I can solve the whole of polynomial hierarchy. I can do it in polynomial time, in fact. So this is why. So you get it right, and in fact now you can. Okay, so let's dissect this. Okay, let's dissect this theorem and sort of chew on it. To say that P is equal to is contained in P to the sharp P. Okay, and says something like, so is a good evidence, okay, for the claim that no pH algorithm for solving sharp P. Take the hardest, suppose, but yeah, take it with a grain of salt. Take the hardest language in the polynomial hierarchy, way up there, okay, because I mean sigma thousand or pi thousand, whatever, okay. Take the hardest thing, instance of that. or the hardest algorithm to solve that, and it still won't be able to solve sharp p. Until now, we've seen sharp p seems to be very way up there. No, it's very close to p space, in fact. Okay, and we're
So
still
I have
not
a
able.
question here.
Yeah.
I have a question here. That can you rewrite the relation in between three things? What is the relation in between Sharpie and NP, and what is the relation in between Sharpie and P space? Then probably the things will become, I mean, easier to understand.
Okay. Okay. Sure. I cannot relate NP with sharp p. Okay, I cannot do that because one is a decision class and the other is a
Counting class.
counting class. So I can only philosophically say that okay, one counts and so one tells the existing of a certificate and one counts the number of certificate and so on. But I can always say that oh, okay, if sharp p can be solved efficiently, then NP can be solved efficiently.
But don't we have such a situation such that NP is a subset of the Sharpie? Why so? Because if we have one solution, then NP, I mean, the problem has already been solved.
Yeah,
Because
but
having count
look
as one. Yeah.
yeah, but look at it in terms of formal mathematics. NP is a set. Okay,
Yes.
NP is a set of of languages. Okay, NP is a set of languages. What is P is a set of functions.
How? Why?
Because
Why functions?
um, yeah, P is a set of functions, right? For example, permanent.
Mm-hmm.
Permanent is not a
Uh,
language. I mean, in a
uh,
strange way, you can think of it as languages, but
yes.
but permanent says what? Permanent is a function simply. You cannot. How do you even tell it in terms of languages in a very straightforward way?
So
Permanent
since yeah,
is a
so since
function.
according to the yeah.
Is defined as some kind of function that you have this summation of product and so on.
Yes, yes. I vaguely remember this permanent thing, and probably it is somewhat similar to determining the determinant of a matrix kind of a
Yeah,
thing.
yeah.
Uh, okay, but since according to the definition of the hash p, we are simulating it. I mean, we are deriving this definition by using the non-deterministic Turing machine.
Hmm,
So it itself says that I mean anything I mean which we are simulating over a NTM,
hmm,
its collection would give us a language.
hmm, hmm, hmm.
So yes, and for some of I mean for a language we would be having multiple number of the solutions. So that count is the Sharpie.
Right.
Yes, and
Okay.
if I have at least one count, so then it shows that yes, the problem which is there in the NP, the corresponding problem which is there in NP has been solved. Like
Hmm,
say if we consider the sharp set and
hmm.
the simple set, so set is the element of NP, and if the value of the sharp set is comes out to be one, so then the problem is the NP is solved.
Exactly. So that is what I was saying with this that sharp p, if there is an efficient algorithm for this, it leads to an efficient algorithm for NP. But since these are sets that have members that differ in with each other. Okay, one is a class of functions, one is a class of languages. Okay, and
Actually, it is difficult to digest that. I mean, probably I'm unable to understand that. So, can you take the example of the sharp satisfiability and tell us that yes, this is the collection of the functions rather than the collection of the strings?
sharp. What did you say? Oh yeah. For
Sharp
example,
satisfied.
sharp satisfiability.
Yeah.
Okay, not in terms of permanent. Let's call it sharp sat. Okay, sharp sat.
Yes.
Okay, takes in some phi. Okay,
Yes.
and what it does is it does a summation
Yes.
over all possible inputs and does a phi of x. This is a function.
Uh, Oh yes, 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 yes. I understood this thing. Yeah,
Okay.
yeah. It's clear. Yeah, yeah. Thanks. Yeah.
Yeah. Okay. So phi is satisfied. Okay.
Yes, yes, yes. Clear.
Now I think it's clear. Okay. So, um, uh, yeah, where was I? Okay, yeah. So this is sort of now again I'm being a very hand wave, but of course you asked again p space and you had also asked what is the relation between p space and sharp p, right?
Yes.
So again I cannot directly say because one is a function, one is languages, but we can of course say that sharp p is contained in sharp, not sharp p space. That's a bit obvious, I think, but it is contained in FP space. Okay. Try to think of why.
Yes.
Okay.
Yes. Yes. Yeah.
Getting it? Okay. So what I actually mean is an FPH algo here. Okay.
Yes. Yes.
Okay. There is no FPH algo for solving sharp P. Because if that was true, then PH would be contained in P to the FPH with Oracle access to FPH. Anyway, um, but these are so many. There could be so many takeaways. But so now I think you understand why this is to the sharp p also. Why to relate these two worlds? To relate these two worlds, why we need an oracle at the top? I cannot just say pH is contained in sharp p. All this the statement here is very close. Okay, p is nothing compared to sharp p and pH. Okay, but I cannot say something like pH is contained in sharp p because one is
Uh,
functions and the other is precisions. Yeah.
uh, yes. Yes.
Okay. So
Yeah.
this is a solution to relate these two to take it as a oracle. Yeah. One.
But still, because if you write a direct relation in between pH and the sharp p, so we would be comparing, say, a collection of the strings, a collection of the languages, say, with the collection of the functions at the most. But it's okay. But then this will lose that freedom of querying to an oracle and which will respond in the polynomial time.
Yeah. That too is true.
That yeah,
That too
yes,
is
yes.
true.
So
Yeah.
so when I write this p raised to the power something, so that raised to the power something I think becomes really very very powerful. That as if it's equivalent in Almighty. I will give him a string, and the Almighty will respond to me in the finite time that okay, this is the answer of this thing.
Yeah. That too is true. That too is true. I mean,
Yeah.
this gives slightly more power in the sense that I'm allowed to make several queries to the Sharpie oracle.
Yes. Yes. Yes.
Yeah. That is true. Else, um, yeah. If you were to make single query, but yeah, okay, fine. Yeah, that is true. That's true. Okay, so we have this now, right? So yeah, so this is Toda's theorem, and this is why it's so important. Also, he won a Godel Prize for this result also, and yeah, this is and it is quite surprising, and so this was a vital step to bridge the gap between counting and decision.
And slightly unrelated question, but then how relevant or how prestigious this Godel Prize is?
Oh, Godel Prize is very relevant. Godel Prize is sort of the Nobel Prize in in theoretical computer science.
Oh, I see.
And
And the Field Medal and Turing Award are different
yeah,
things.
they
Is
are
this?
different. So Turing Award is for general CS. Okay, you could even do with, for example, what is the name of the person who made the internet?
Ele- uh, internet.
That
I
Short
forgot
name.
his name. Yeah, Larry Page. No, no,
No, Larry
no,
Page
not
was
Larry.
Google.
Is his name starts with S kind of the thing. I forgot his name.
I thought it was Tim something.
Tim. Yes, yes.
Right?
Tim Berkeley. No, Tim Berkeley. No.
Yeah, it's Tim something, I think. Whoever made the internet. Yeah. Okay. And
Yes.
this person works in networks and stuff, right? The person who made World Wide Web is also separate, and he also got a Turing Award from what I recall. And there is uh, uh, the person who made neural networks. uh,
Hinton. I think he was Hinton. No, not Hinton. The one who gave the idea of the threshold.
yeah, probably. So that his name I don't recall at all.
Okay.
And but of course, I think since this is getting recorded, probably we should also give the credit to those people. uh, Internet founder Tim Berners-Lee,
Yes.
and the other is what did I say? Um,
WWW founder.
yeah, www founder. Okay, it's the same guy. Oh
Same,
yeah, the
same
intern.
guy.
Okay, wait, I thought they were different. Okay, one. Okay, sorry. One was responsible for making this, OSI layer, network layer, and stuff, and the other was World Wide Web. Okay, and the
Yes.
final one I was talking about was neural network inventor Frank Rosenblatt. Yeah, so he also got this Turing Award, and if I think you must have heard of Donald Knuth,
Yes. Algorithm person. Yeah.
algorithms person. Okay, he's a guy from
Yeah.
theoretical CS. Okay,
Yes.
and there's this another guy called Leslie Lamport. He has done both work in theoretical as well as networks and stuff, and distributed computing and so on. He has gotten a Turing Award, and recently, okay, this is nice. Okay, it's um, recently Avi Vigderson this year.
He's from cryptography side. Not
Not
cryptography, but probabilistic proof. I think.
Yeah, he has done works in probabilistic proofs. He has done in communication complexity. He has given important contribution to complexity theories.
Yes.
Okay, for pseudo random generators and so on. And he is from Israel, and he had gotten the Turing Award this year. Okay, he has given an
Yes.
important contribution to the field of complexity, which is called the uh, KW schemes or KW theorem. Okay, you'll learn about it in the next week. I probably think so because next week there's communication complexity uh,
Okay.
in this course. Okay, but yeah, recently a complexity theorist this year got, and there are several complexity theorists who've gotten the Turing Award in the past. Okay, but Turing Award is in general in just for CS in general. It could be networks, AI, whatever. Okay, and Gödel Prize is for theoretical CS. And in 2006 or 2006 or 7, this Manindra Agarwal and his team got.
AKS algorithm. Yeah. I
Yeah,
remember. Yeah.
so they got the Gödel
Yes.
Prize. And very prestigious. For theoretical CS, it is equivalent to the Nobel Prize.
Okay. Okay.
And Turing Award is equivalent to Nobel Prize for CS. And Field Medal is for general mathematics. And there are people who have gotten the Fields Medal for theoretical computer science also, because it's very closely related to pure mathematics.
Okay. Okay.
Yeah. So yeah. Okay. So let's continue. Where were we? Um, uh,
Toda got the Gödel Prize. I mean, for this
oh
important
yeah.
result, and
Right.
THS. This. Yeah.
Right. Okay. Okay. So anyway, Toda got a Gödel Prize for this result, and this is why it was massively important. And Now, looking at Torah's theorem, let's solve a question. Okay, here's a simple question. Okay, so here's the question. Suppose there's a polynomial time algorithm to solve sharp perfect matchings, then which of the following become true? Fp is equal to sharp p, ph is equal to p is not equal to np. Okay, wait. P is not equal to np. And finally, p space is equal to p. Okay, I'm coming. I'll just get some water. Okay. Sorry, looks like the this has a
Question is not visible.
yeah. Sorry, this my iPad has a this screen sleep setting. So after some time it went. Oh, it's in low power mode. That's why. Okay. Yeah. Anyway, sorry.
No issues. Yeah. So is this perfect matching problem a Sharpie complete problem?
Yeah, it is.
Okay. Okay.
So
Okay.
it
So
so the proof was done in the was it done in the lecture? I think it was done in the lectures.
uh, okay.
Yeah, yeah.
So if the perfect matching is a Sharpie problem, and if we can solve this problem in the polynomial time, then it means that all the problems which are there in the Sharpie can be solved in the polynomial time. And so it means that yeah, I can count the number of the solutions in the polynomial time, and if I can count the number of the solutions in the polynomial time, then I would be able to search the solutions in the polynomial time. There is no other way. I mean, I think that there won't be any other way. So therefore, the option A would be correct. That FP is equal to the Sharpie, And if I can count the number of the solutions in the polynomial time, so then according to the Toda thing, I can query to p raised to the power p kind of a thing, and that would be same as I mean p only, I think. So therefore ph would be equals to p then. And third option is that p is not equals to np would become a certainty, because np at the most would be maybe viewed as a subset kind of the thing of the sharp p. And since now the sharp p can be solved in the polynomial time, so this would but then sharp p means the non-deterministic thing only. But we do have a polynomial time to solve this problem, the perfect matching. So this will indicate that. So I'm a little doubtful about this C thing. But then this P space then would be equals to P in the sense that no, as far as the P space and P is concerned, so I'm not sure that just because I can solve this perfect matching in the polynomial time, it has some anything to do with the space occupied. So I'm pretty sure about A and B and not sure of C and D then.
Okay. Yeah, let's see. Okay. Suraj, any guesses? Oh, okay. Hi Suraj, is it audible to you? Okay, but he might be facing some internet. Okay, yeah. Yeah. So let's look at it. Okay, FP is equal to sharp P. Suppose there is a polynomial time. Uh, Algorithm to solve sharp perfect matchings. As soon as you say that there is a polynomial time algorithm, okay, by polynomial obviously we mean deterministic, okay, time algorithm to solve sharp perfect matching. A deterministic polynomial time algorithm that solves the search problem, okay, or counting problem, whatever, is exactly what FP is. So as soon as you have that, trivially sharp P is contained in FP. Right. Now that you have that sharp P is contained in FP, and you know that sharp P contains FP. Okay. Also, FP is contained in sharp P. Okay. And we'll look at this why later on. I have a separate question for this, but it's not very difficult. Okay. Maybe meanwhile think at the back of my mind why this is true. And so sharp P is equal to FP. Okay. Next, pH is equal to P. Now, yeah, you're right. We are going to use Toda's theorem. What does it say? It says that pH is contained in P to the sharp P. Now, sharp P is nothing but contained in FP. So, pH is contained in P to the sharp, P to the FP. Now, any computation that FP does, we'll do it ourselves. Okay, we'll do it ourselves, and since it can be done in polynomial time. So let's say this is the, and on the way P makes queries to the FP oracle Q1, Q2, Q3, and so on. It makes queries to the oracle. Compute this in polynomial time. Compute Q1, Q2, and so on in polynomial time without the oracle. So total time is some polynomial, because it's polynomial number of queries, okay, times some polynomial. So it's still polynomial. which implies that pH is contained in F. What F? Sorry, pH is equal to P. And let's look at C. So the first two is correct. Oh, one moment, okay. I'm not able to. Okay, yeah. And first two are correct. Final one, P is okay, not to final one. P is not equal to NP. This is the question there, right? The fact that pH is equal to NP, pH equals P, this implies that NP is contained in P because pH contains NP also, right?
Yes. Yes.
If
Yes.
yeah, yeah. Therefore, P equals NP, and this one is wrong. And D, which is P space, is equal to P. This will still be open. P space will not be affected, or at least there is no trivial reason why P space could be affected, because P space
Yes.
seems, yeah, right. P space seems to be a bit aloof from all this, because using Toda's theorem, the most you can say is about pH, which is contained in P space. But can you say that P space is contained in P to the sharp P? Can you improve Toda's theorem? That is not known until now. Maybe it is possible, but it is not known until now. Okay.
Yeah. Probably something can be done for the log space classes, and if not p space,
Log
like
space
say
plus.
Immersman, that thing that we say that NL is equal to co-NL kind of the thing.
Yeah,
Because
I was thinking about that when I wrote this question, but it seems like log space. You know, you have this p space, okay, and you have this pH, and you have this L. So the collapse is happening sort of here. Okay, L is not really getting affected by it, because the fact that P equals NP is not going to affect L and L and whatever.
yes,
They are
yeah,
sitting very aloof from these people. So
right,
it looks like it is unlikely that anything will be affected in these small classes,
yes.
right? Okay, sure. So yeah, so that is this question. Now addressing this question, FP is contained in sharp P. Okay. Yeah. So this is the same question. Show that fx, if fx can be computed in polynomial time, then fx is in sharp P. Okay. So think about it for once. Then I'll.
How is this related to the previous question then? Because it simply says that can I, if I can compute fx in the polynomial time. So if I can compute fx in the polynomial time, then I would be able to count non-deterministically.
Yeah, yeah. Before
I
that,
would be
before
able
that,
to.
before that, how is this related to the previous question? That is, FP is contained in sharp P. This is the question, and I'm saying it is same as this. Why is it so? What is FP?
Uh, so FP means that I mean we can search the element in the polynomial time. I mean
Yeah,
this
not
is a
not not just
search.
not only search.
Yeah.
You can compute the function in polynomial time.
Oh, I see. I see. Okay. Okay. So does this mean that any function which can be computed in the polynomial time, I mean, so if the calculation is possible in the polynomial time, then what else we required in the sharp P? We have been
Exactly.
given a NPM non-deterministic Turing machine, and which can So which can, I mean, Sharpie means that how many verifiable solutions exist,
Right?
and we can, yeah. So and we can verify so we can count the verifiable solutions at the polynomial time.
Hmm.
Okay.
And that should be exactly f of x.
Yes. Yes. Yes.
So just a moment, I'll turn off the power saving mode. This is causing the screen to shut down. Yeah, over. Okay. Anyway, yeah, let's get back. Uh, yeah, fx can be computed in polynomial time. Means that f is in fp. Okay, so this simply means
Yes.
that fp is contained in sharp p. So yeah, so well you were saying that. Okay, so what is sharp p? Sharp p means if fx is in sharp p, it means there is a Turing machine where the number of accepting states, accepting paths is exactly f of x.
So I mean to say that the meaning of the Sharpie would be that deterministically we can count the number of the verifiable solutions. I mean, because verifier works deterministically even in the case of NP. So once you give me the solution, I can verify the solution in the polynomial time. And now the meaning of the Sharpie would be that I have a machine which runs deterministically in the polynomial time, and I can count the number of the I mean certificates in the polynomial time. So if I can count the number of the certificates in the polynomial
No,
time,
no, 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 no,
won't it
no.
mean
Why,
that,
why,
yeah,
why
I can?
count the number of certificates in polynomial time? It should be non-deterministic polynomial. No, first of all, you are not counting the number of certificates directly. You are not going 1, 2, 3, and so on. It is true that um, sort of exp contains sharp p, okay, or fexp contains sharp p because you can go over each assignment, each certificate and then count it. But sharp p, there is no straightforward verifier definition for it.
So then, what is the definition of the Sharpie? I mean, which you wrote in the beginning of the session.
Sure, I'll come back to that. Fx is in sharp p if there exists a non-deterministic Turing machine M such that for all input x, okay, M has fx many accepting paths. Okay, when you
Yes,
run it
yes,
non-deterministically, the number of accepting paths are f of x many. It's accepting paths of M on input x is represented by this hash accept mx. Got it?
yes. So yeah, so yes, and Turing machine is non-deterministic, and Turing machine has fx many number of the accepting paths. Okay, okay, yes,
So you need to make a Turing machine, construct a Turing machine that have fx many accepting paths.
yes,
Okay.
yeah, right.
So okay, I'll write it. Okay. So 1 minute. F is in FP. This means that there exists a deterministic Turing machine computing f of x on that input x. Okay. Let me call it M. Okay. So here is a sharp P algorithm to compute f of x. Okay. F. Okay. What is the input? X. So what is the first step I do? First step I do is I run x m on x. Okay. What is the output? Output is f of x. M, when you run m on x, by definition of m, it computes f of x. And why does it compute f of x? Because f is in fp. Now, what is the next step? What do? You want to run that. Now, this Sharp-P algorithm, this is non-deterministic. What you want to do is you make sure that when the algorithm runs, the number of accepting paths is exactly equal to f of x. I'll call it f.
Right.
Okay. So that is all you need to do. Now, what you do is now you what you do is I'll say now you start the non-deterministic process. Okay. How do you start the non-deterministic process? You guess, okay, a string y in 0, 1 to the okay, let me not write it as a string. Okay, guess a string as a natural number, okay, n in 1, 2 and so on, okay, 0, 1, 2 and so on till f of x plus 1, okay, and 3 if n is at most, or actually since f of x is, since we are guessing from 0 less, okay, so let's not make matters complicated, so is less than equal to f of x, then accept, else reject. Okay, or you could have made this algorithm that always
Yes.
So on exactly f of x many certificate, it will accept. Okay.
Right. Yeah.
Yeah. So therefore, fp is contained in Sharp-P. Okay.
Yes. Yeah.
Right. And okay, good. Okay, it's almost time, so I'll just show this question. Okay. Now we know what Sharp-P is properly. That it is the number of non-deterministic paths that accept. So try this. Okay, let's try the first one. Show that if f1 and f2 are in Sharp-P, then so is g equals f1 plus f2. On adding to
That
yeah.
yes. That seems to be straightforward, because if I have f1 number of, if f1 is in Sharp-P, then non-deterministically I can have those many paths, those many accepting paths.
Now the non-deterministic paths, number of accepting paths should be the sum of the two original non-deterministic paths.
So what is this? G, because functions. This is the addition of the functions only.
Yeah. G is addition. G is still a function, right? G
So I
of
can always,
x is defined
yeah,
as f1 of x plus f2 of x.
yeah, right. So since f1 of x is there in the Sharp-P, and so I would be having f1 of x number of the accepting paths, and f2 for f2x I would again be having the f2x number of the accepting paths, because probably I am not generating a new problem. So what could be the meaning of the g of x is equal to f1 of x plus f2 of x? I'm not generating a new problem. Whereas in the case of the multiplication,
No, you are still generating a new problem, right? But how do you do this using a Shapley algorithm? How do you make sure that the sum of the number of accepting paths is the sum of f1 and f2's f1 and f2?
why so? Because f1x and f2x have no relation. I'm just adding. I mean, how will I perceive this g of x? Is this a new problem, and which is the addition of the two existing problems? Like say f1x could be the satisfiability problem, and
No,
f2x
no, 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 no. These are functions, not languages.
these are functions, right? So yes, so I mean, I can
I know
always
what you are saying, that oh, since f1 and f2 both have algorithms, I'll just add them up and do sort of like what I did before.
yes,
But f1 and
yes.
f2 have Sharpie algorithms. That particular algorithm does not, while the run of the algorithm occurs, it does not know what is the count. It just knows that, oh, okay, that when I finish the run, the number of accepting paths will be. The algorithm itself does not know the count. Some outsider, when it looks at the branching and then counts the number of accepting paths, it will be equal. You get it what I'm saying?
Oh yes, so I can include a facilitator kind of the thing here, that sometimes it runs on the F1, sometimes it runs on the F2, and
Right.
then finally we do some merging
Exactly.
kind of.
Exactly. Yeah. Yeah. So how do we build that facilitator?
Oh yes, so I'll check. So I'll have to follow either of the path. That
Right.
is yes. And how will I decide that whether to follow which path? So from the X, I will identify that whether this thing belongs to the F1, to the first thing, or to the second thing. And accordingly, I can design this facilitator thing.
You are very close. Okay. You are very close. Okay. So this is finally, this is what I think we both are imagining the same thing. So this is for f1 and this is for f2. Okay, this is machine M1's run, this is M2's run, and there are accepting paths and there are rejecting paths, and this is number of accepting paths of M1 on X is equal to F1 of X, and this is number of accepting paths of M1 on X is equal to F2 of X. And here, this is the facilitator that you are saying, right? This final non-deterministic machine, which I will call M, okay, on input X will have F1 many accepting paths plus F2 many accepting paths. Okay,
Yes.
right. So this is like sort of branching out. And this is M1 and this is M2. It makes non-deterministic S. There's only one thing to add here. So what I'm doing is, there is on the left branch I'm running M1, on the right branch I'm non-deterministic running M2. Now this was what you are asking, which one do we decide what to run? You don't need to decide what to run, because you are, if you look at observe this, what you are essentially doing is you are non-deterministically running M1 or M2, right? You are non-deterministically choosing whether to run M1 or M2.
Yes. Yes. Yes.
Exactly. So here's the final algorithm. Here's Sharpie algorithm M on input X. All you need to do is um, non-deterministically choose, um, let me call it B, between 0 and 1. If B equals 0, run M1. If b equals 1, run M2, and that's it. This is b equals 0, b equals 1. This is the non-deterministic case. Is that clear?
Yes, yes.
Okay. So this is what I meant by the Sharpe algorithm itself does not know what the count is. Okay. It just knows that when it halts, the all the possible different accepting paths as equal to f of x. Yeah.
Right, right, right. Yeah.
So now the next part is that the product is also in Sharpe. So similar logic. Can you think of why what?
So yes, yes. So probably I will then go for some serial combination kind of the thing instead of the parallel one.
Oh, you're right. Right.
Yes.
So what we'll do is here the idea is that I have M1 which computes F1, remember, and it has accepting paths, and this number of accepting paths is equal to F1 of x, and there are rejecting paths. What I do now is on each accepting path I will run M2. Alright. On each accepting path I'll run M2, and M2 has some accepting paths and some rejecting paths. But what we know is that number of accepting paths, okay, and this is M2, all of them, and number of accepting paths of M2 of x is equal to F2 of x. So this is equal to F2. This is also equal to F2. Okay. So what is the total number of accepting paths? That is number of accepting paths of machine M. I'll call this entire machine M.
F1x into F2x.
Exactly. Of M of F1x is equal to number of accepting paths of M1 on x times the number of accepting paths of M2 on x, which is equal to F1 of x times F2 of x. So this is how you can compute the product. So what it means, I won't write the algorithm. Okay, now I think it's straightforward. What it means is that since these are functions, okay, on natural numbers, it is natural to think about additions and subtractions. Additions and multiplications here. The fact that if functions are in Sharpe, then additions and multiplications are also in Sharpe. So inductively, you say that any polynomial you can compute on Sharpe functions will also be in Sharpe. Okay,
Right.
right. So that is the takeaway from this. But it's okay. It's almost 8 o'clock. So if you have any other questions, then you can stay back and let me know. Else we can call it a day. Okay. So next week we'll be dealing with communication complexity. Yeah. Any
Yeah.
questions?
So
Go ahead, Suraj.
yeah.
Yeah.
Yeah. So why this counting thing is important? So
Why
did
is
you understand why this counting thing is important? It is
counting?
important. So why this? I mean, counting complexity is important. P is
Uh,
important, but then why this sharp P is important?
oh, why? Okay, because a lot of real world problems don't always deal with yes and no. A lot of problems deal with um, counting, and counting and search are not very different. Okay, and a lot of real world problems actually depend on searching, and
Yes.
And there are, I mean, lots of counting problems in real life. Because, for example, um, um, I look at Facebook, okay,
Hmm.
and I want to count the number of customers, the average number of customers who are most valuable to me. I look at stocks. I want to count the number of um, stocks that are relevant to me, and so on. And these counting problems occur everywhere in computational in real life. And search problems are also very close. So we are interested in FP and so on also. And if it so happened that counting problems were easier or at par with decision problems, for example, if sharp p was as easy as deciding p, okay, we already saw that if there is an efficient search version, then there is an efficient decision version. That is fine. But the fact that we can have a hard search version but an easy decision version, now that means that these counting problems are already non-trivial. Okay, we cannot just keep a blind eye at them because we can already do decision versions. Now this is why it's important. And the fact, the fact that we have fact is that there exists problems L in P such that sharp, I'll call it A, such that sharp A is sharp P complete, is what is most amazing about this, that it is easy. Decision version is easy. The counting version is hard. That is the most amazing thing about it. Because, okay, fine, SAT is an NP, SAT is NP complete. It is already hard. And then we can imagine that, okay, sharp SAT is already hard. It is sharp P complete. But the fact that, we have problems that are in P and yet their counting versions are also hard. They are sharp P complete. And permanent is one example. Counting perfect matching is an example. You can verify if a graph has a perfect matching in polynomial time. You can not permanent. You can do two sat. Two sat is a good example of an algorithm in P. All of these are in P, but surprisingly, their counting counterparts are sharp P complete. They are very difficult. Okay.
Yes, yes.
So there is, yeah, right. So there is a lot of non-triviality in counting, and we have not understood it properly yet. So that's why it asks us to, okay, we should, this is probably a question worth pursuing. Okay.
Yeah, yeah, yeah. Thank you for such a nice session. I learned lot many things about this counting part, which I was not knowing earlier.
Oh, okay,
Thank
sure.
you so
Sure
much.
thing, sure
Uh,
thing. No
Thank you
problem.
so very much. Yeah,
Okay then. Okay. Okay. Then any other questions?
yeah.
Okay.
Okay then. Yeah. Good
Okay,
night
no
from my
problem.
side.
Okay, go ahead. Good night. Good night. Okay. It's
Bye bye.
okay, bye. Suraj, any questions? Oh, okay, sure. Oh, okay, Suraj. Okay then. Good night then. Bye bye. We'll all have dinner.